Good morning. Welcome to Krishna's class. In the last couple of lectures, we have considered L1E and LP or L infinity. In fact, our plan was to consider LPE for one less than or equal to P less than or equal to infinity. And out of this, we have already shown that L1E and L infinity non-linear. So what remains is this. We now take up LP for recall that I made a statement beginning that it's not something very easy like in the case of L1E and L infinity. Here we need some extra machinery to work this. That means we have to do some powerful inequalities which have to be used in the process of proving this, the normed linear space structure of LP. So our task is now to work on this. Okay. So we start with the following definition. For a measurable set, E and 1 less than P less than infinity and a measurable function we define norm of F P find on E such that mod Fp is integrable set this equal to 0. Now in fact, so we make a remark. We have been talking about using the notation P, where F designates the element of F tilde consisting of all functions F. That is, this was our definition. In the sense, now the meaning of this is that gx equal to fx all for almost all x. Now that is the definition of this. Now we found that can be made into a linear space and into a normed linear space, but henceforth we shall simply write to designate the class so that's something because we have to keep on repeatedly writing this. So to avoid that, we will simply write this. Therefore, this part, this we will designate as that's a bit. Or simply write is the notation for that's the new notation that we adopt so that we don't have to repeatedly put these brackets over and over again. But one should clearly understand that we are talking about the equivalence class of functions or elements of F tilde. That's what we are talking. Now, for functions, measurable functions F, whose pth power is integrable over E, we can define norm F P. That is now we prove that Oh, we have already done it. So those two cases we need not consider. So we will work on this. LP, we have LP. LP is all the equivalence classes of functions f finite. We have seen that this is a linear space. No, we have not seen. We have to show that this is a that requires the following. What are the things that you have to prove? This collection has a zero element. Okay. And we have to show these two things, namely and we have to show that this is what we have. So this requires, so let us examine one. Okay. One requires to prove f belongs to that is norm finite. Or that's exactly what it is. This is something not trivial. So that probably requires a some work. Okay. The second part is relatively simple. Integral over E is finite. Therefore, so that is there, but the first one requires some work. So you have to prove this. Okay. This we establish by proving the following. So to prove the first one, hold on. We show that once we prove this, it's a basic property of the norm, the result would fall. So this is what is called the Minkowski inequality. Supporting results. So let us prove this. In fact, we prove that norm P, norm F P defines a norm on LP. So what are the things that you have to prove? The first thing that we verify is this. This is non-negative. See, this is a functional. See that F2 so this is a functional. Now the first thing is non-negative. F equal to 0. Now here this essentially means, okay, I'll make some detailed remark about it later while proving this. Now norm F P is greater than or equal to 0. Now this is obvious by the definition. Now it remains to show that norm F P equal to 0 implies that is Fx which is the 0 element. Okay, so let's prove this. Now which happens if and only if F equal to 0 almost everywhere 1, and this implies F is 0 function, that is the block F. Okay, and by our notation this we have designated by F itself. Okay, so this implies the zero element of LP. That means the class or F is the zero element of so that completes the proof of this. Now the second thing is positive homology. That is now this is obvious. Already discussed. Now the third one is the more difficult one. The third one is what you call the following results. That is F that means we have to show that norm of F plus G okay. Now this is called the Minkowski mean. It was easy to prove this. Now we need some work for that. So let us start build the necessary machinery for that. So we define open interval 1 to infinity. Then Q we define as P divided by this is when Q is uniquely defined. Infinity. Q is called conjugate of P. Q is called the conjugate. Is the term. Then what we can immediately verify is that 1 by P plus now this relation, that's Q and P have the same sort of status. Okay, P is the conjugate of Q, Q is the conjugate of, that's what I mean. Same status. Now we prove some nice inequalities which have much deeper ramifications than used as a tool to prove this result. It's useful in proving this result, but beyond that, there's a lot of ramifications. In fact, when you come to talk about the conjugate spaces, this will be very relevant. We are not going into that. It's one of the beautiful results that you are going to do. Okay, so we have a string of inequalities. One is called the Young's inequality, which in turn helps you to prove what is called the Minkowski inequality, as well as there is the Holder's inequality, which is a generalization of the Cauchy-Schwarz. So all these are very fascinating. In fact, one can go very deep in all these things later, but let us start with this. Like these LP spaces are very fascinating. Our objective is something different. Our objective is the following. We want to prove that LPE is a normal space. Okay, that's our objective, right? And then what we do is we go further and show that it is of course a metric space. Obviously, every normal linear space is a metric space. Not only that, it's a complete normal linear space or a complete metric space. This is our objective. So that the mission that we have taken up, starting from Riemann integration and then modifying it to introduce the measure, etc., to get more functions into it, turns out to be a grand success. And that's why this measure and integration theory is a remarkable piece of mathematics that was created or discovered in the 20th century. Now we have the following definitions also. The conjugate of one is as infinity, and the conjugate of and this again, one you look at this relation equal to 1. If you want to keep this relation intact, if you let p go to 1, then 1 by q goes to 0, and that's possible. Q non-negative, so q goes to infinity. And when p goes to infinity, then what happens is 1 by q equal to 1 and q equal to. So that is the extension of the concept of conjugate numbers defined earlier to p equal to 1 and p equal to infinity. So now we are in a position to introduce Young's inequality. This is one of the basic tools that we use for infinity. The conjugate of p and for any two positive numbers A and B. We have AB is less than or equal to let us prove this now. Proof is very simple. Uses some elementary calculus. So we define the function x. So this is the function that p, q, etc. are as we have defined. Now this we define x positive. That's pretty obvious. I mean, in fact, if you want to prove this, we'll prove it as follows. Observe that so g dash x is negative whenever x belongs to y. And g derivative of at 0 at 1 equal to 0. And further, x belonging to 1 to infinity. So on the entire interval 0 to infinity, we have now looked at g derivative. Okay. Now you see that okay, let us see what is g0. G0 is equal to 1 by q, which is positive. Takes a positive value. And g1 equal to 0 and g derivative of x is positive on for x belonging to 1 to e. Now this is what we have established, which implies g derivative of x is greater than or equal to 0 on infinity. So what happens is that this function is taking the value something like 1, takes the value 0. So the property that you have is that g derivative x is negative means g is decreasing. So this is 1 by q and it just decreases to this place and then it increases. Now this is the property of g. Okay. So this is at 1 and from here onwards g derivative is 0. So g is, this is y equal to gx. Right? Therefore, we have g derivative of x is greater than or equal to 0 on this one, which implies gx is greater than or equal to 0 on 0. Now this is the important. Okay. That is, what is gx? 1 by p which in turn implies Okay. What do we gain out of it? Now we take x naught, a specific value of this, which is equal to a divided by b to the power minus. Then what we have is, now this is certainly a positive. Then g of x naught equal to one by p a to the power p divided by b to the power p divided by q minus 1 plus 1 by q minus minus 1. That is g x naught. And this, if you compute, and this is positive, because x naught is great, so it is positive. Therefore, let us work on this. Therefore, what you have is a to the power p by p into b to the power q minus 1 divided by p to the power p from this relation. Get this. Greater than a. Therefore, we have, if you simplify this is what you get. To simplify this, now use then what you end up with is this. Then what you end up with is this. AB is now in this context, I think we'll just look at this function. Just not necessary though. So you call define. So that proves the inequality. That's the end of it. Now define hx equal to hx minus x. Now you see that h0 is What is the reason? This is because now you can actually plot the graph of h. See, this is x. Compare with x. What happens is this is some point h into h0 equal to 1 by q. It starts from 1 by q, which is positive. And then at 1, this takes the value 1. So you see that this, in fact, this is the graph of h. So h always stays above the line x equal to 1. This is x equal to, this is y equal to x, this is y equal to 6. So you see that it always stays above this. Therefore, for any x, see, hx is greater than infinity. So this inequality we make use of. Hx minus x is positive. So we make use of this, and that's what we have made use of. Okay, thank you very much. And I think we conclude here, and then we take up Holder's inequality and Minkowski inequality, possibly in our next lecture. So, thank you very much.